Hello, chemistry students. We continue our unit now talking about acids and bases. It is going to be a bit of a review from grade 9 and 10, but we will add another definition to your idea of an acid and base. Okay, but a bit of a review first, a few characteristics of each. Typically acids have, of course, a sour taste. Think of that lemon or orange. And bases tend to taste bitter. For acids, there's no characteristic feel, it just feels watery. Bases, think of soap. Soaps are usually a little bit basic and they feel slippery. Now, using litmus paper, we can see that in acids it turns blue litmus paper red and it turns red litmus paper blue for bases. So acids also typically react with most metals, not all, but most metals to produce hydrogen gas, whereas bases don't tend to react with metals. Again, most metals. Okay, now the definition that you might be used to, and maybe you don't know the exact name of the definition, but here it is. It's the Arrhenius definition of acids and bases, and this is what you've been taught maybe since grade 7, 8, and certainly in grade 9 and 10. The idea that acids produce, right, when they ionize, they release hydrogen ions, in other words, protons, right? And bases ionize to produce hydroxides. So I know you've been exposed to acids like this, hydrochloric acid, or an oxyacid, sulfuric acid, right? We know that these will ionize to produce that hydrogen ion, right? And bases, probably one that you'll recognize is sodium hydroxide. And again, this will ionize to produce that hydroxide ion. Right, so that's the definition you're used to, perhaps. I'm going to add on to this, and I'll explain why we need to do that now. Okay, but before we do, hydrogen ions are so reactive that they will react with water itself. So H2O will be protonated, it's called. Right, will react with that hydrogen ion, that very reactive hydrogen ion, to produce another ion called hydronium. Okay, and this is actually what mostly exists inside any kind of acidic solution. So we'll see that everything here is a 1-to-1-to-1 ratio. So in your pH formulas, so a bit of review also on your pH formulas, you often saw a pH formula written like this: negative log of the concentration of hydrogen ions. That's the same thing as writing hydronium. Right, so whatever concentration you find of hydrogen ions essentially can be spoken of in the same terms as a hydronium concentration as well. Okay, moving on. So there was a problem with this definition about a century ago. Ammonia is not your typical base. It doesn't look like that sodium hydroxide. It doesn't have that hydroxide ion. And yet it forms a base in water, and its properties when in a solution of water are basic. So this definition had to be fixed. Maybe I shouldn't say fixed. This definition had to be amended. We had to add another idea to the idea itself of acids and bases. So here it is. An English and Danish scientist, Bronsted and Lowry, they added to these definitions, and now it is still correct to say the Arrhenius theory is correct, right? It certainly does. Acids certainly are acids if they release hydronium ions, and bases if they ionize to release hydroxide. But this now is an addition to that. So acids donate hydrogen ions, simply put. So anything that can donate a hydrogen ion can be considered an acid, and bases will then do the opposite. Instead of donating hydrogen ions, they will receive hydrogen ions. Right, so anything that can receive a hydrogen ion can be classified as a base, and I'll show you examples in a bit. Okay, essentially acid and base reactions involve a transfer of a proton or a hydrogen ion. So this transfer of a hydrogen ion from one substance to another is what allows this definition to take place. Again, we're going to see examples in just a moment. Okay, so here we are. This can act. This CN, right, remember your polyatomics, is cyanide. This cyanide ion can react with water, right, in a certain way. Now, this is typically not your standard type of Arrhenius base. It doesn't have that hydroxide ion. Yet, if we compare now, look at this base here. Okay, we're classifying it as a base only because at the moment it just says base underneath it, but let's see why. So we compare this to, we can think of it as its cousin or its conjugate, right? Its pair. You can see that the difference here is that this cyanide has now taken up a hydrogen. Now that matches the definition, the Bronson-Lowry definition of a base. It now has accepted a hydrogen. That makes your cyanide ion a base. And its pair is always the opposite. This is a conjugate acid. So let's go through this. A conjugate base, that's talking about this guy here. Okay, let's talk about that one. So this acid, water, yes, water is behaving like an acid in this case because it's following that Bronsted-Lowry definition, where if it donates a proton or donates a hydrogen ion, look what's happened to it. Its conjugate is OH. That has lost, in other words, water has donated, it's behaved like an acid, it's donated that hydrogen ion, and so now it looks like OH. So we were talking about that conjugate base. So conjugate base referring to this guy over here, to the hydroxide of an acid. So look, it came from an acid, is a substance left when an acid donates a hydrogen ion. Okay, so that's your conjugate base. And then the opposite, we initially started talking about a base. So a conjugate acid, now talking about this guy here, a conjugate acid of a base, yes, it did come from a base, is the substance left when a base receives a hydrogen ion. So this is your base, it received a hydrogen ion, it is now a conjugate acid. So it will become important for you to be able to classify in a reaction like this, which is your acid, which is your base, and which are your conjugate acids and bases. Okay, a little more to add on to that, to talking about acids and bases. When we say that an acid or base is strong, what that really means is that it completely or almost completely ionizes. I'll give you an example here. If something is considered, if an acid or base is considered to be weak, it's thought to not completely ionize. Okay, this definition is defined more clearly perhaps in grade 12, but for now all we need to say is if it completely ionizes, then it is strong. If it does not completely ionize, then it is weak. And how do you know? Well, I'll tell you during a question, or I'll give you enough information for you to be able to determine that. Okay, so here's an example. A strong acid, okay, so this is H2SO4, and yes, this should be a subscript. So H2SO4 at a 2 molar concentration. You know, I'm going to change this. I'm not going to say 2 molar, I'm going to say 0.5 molar concentration. We'll have a pH of, right? So that's our question. So let's quickly figure this out, a bit of review as well. All right, so we know that our pH formula looks like this. pH is equal to the negative log of the concentration of hydrogen ions. And H2SO4 is going to ionize H2SO4, aqueous, your sulfate ion. Okay, so following our mole ratios here, if we have a 0.5 molar concentration of sulfuric acid, because it's going to completely ionize, it's going to multiply in this case by 2, right? If we're following stoichiometric ratios, then 0.5 times 2 is 1. So our concentration of hydrogen ions is 1. Right? It follows a 1 to 2 ratio, 1 to 2 ratio as you're used to. Okay, so now a pH then, let's figure out what the pH is. So negative log of 1 is just 0. All right, so the pH of this sulfuric acid solution is 0. That sounds right. It's very, very low. It's quite acidic, and it's a strong acid because it completely ionizes. Now a weak acid, made one up here, it's H2A, let's say. This H2A also ionizes in a similar way. It is a diprotic acid, we'll get into that a bit, but it essentially just has 2 protons here, 2 hydrogen ions. So this will dissociate in a similar way to sulfuric acid. Aqueous, I should write, then it has 2 hydrogen ions and 1 A ion. Actually, that's -2 there. Okay, and aqueous here and aqueous here. Now, this is what makes this a weak acid. And I would have to in some way give this information to you, or the question would have to give information like this to you. So here it says, and again, I'm going to change instead of making it a 2, I'm going to make it a 0.5. So if this has a 0.5 molar concentration, this weak acid initially, and if it ionizes, what will happen is you would expect, if it weren't a weak acid, if it were a strong acid, it would ionize just like the sulfuric acid. It would be 1 mole per liter because it's a 1:2 ratio. Now, a weak acid will not completely ionize. It will stay in this form, H2A. And let's say, I'm making this up right now, but let's say we get a 0.2 instead of a 1 molar concentration, not all of it ionizes, and we get a 0.2 molar concentration of hydrogen ions. Okay, so now let's figure out the pH with a 0.2 molar concentration, negative log concentration 0.2, and we get 0.7. So we get a 0.7 pH for this weak acid. So yes, it is very, very slightly more basic than this acid here, than our strong acid, but it's not easy to tell by pH if an acid is weak or is strong. That's why you have to look at how much of it ionizes and its difference in concentrations compared to what you would expect given a stoichiometric ratio. Okay, let's move on. Again, I mentioned the term diprotic acid, and that essentially just means an acid with 2 protons. Work backwards now. A monoprotic acid means an acid with 1 proton, right, like HCl. A triprotic acid is one with 3 protons, not too hard there. We can also say polyprotic acids. That's generally referring to anything more than 1. So diprotic, triprotic, they are polyprotic acids. So just some definitions here, some terms that are important to know. Okay, now water. Water is an interesting example. Water can act as both an acid or a base. So I'll give you an example of how that happens for both cases. So water as an acid looks like this, can look like this. So H2O plus HCl. Sorry, where's my eraser here? I'm gonna have to scratch this out. Okay, so as an acid, water, I was jumping into the base example, and that would have been wrong. Okay, so water with ammonia will react like this to produce ammonium. Okay, so what's happening here? Where are the conjugates? So H2O turned, let's see if I can write with this. My pen is acting up here. Let's see if I can fix that. Okay, I'm gonna have to just point for now, and I'll see if I can get this to start to work. So water here, if we compare it to OH, right, what it became, we can see that it has given up a proton. It's given up a proton to ammonia. Now, oh, it just did everything all of a sudden. Okay, so water has turned into hydroxide. It's given up a proton, and it's given it to ammonia, which has become NH4, right? Okay, so let's see about erasing some of this. Pointer options, erase all ink on slide. That's better. Oh, I erased everything. Okay, let's quickly write this down again. Okay, ammonia. Okay. Okay, so water and its conjugate, we can see that it has given up a proton. So water is an acid in this case, and of course an acid produces a conjugate base. Ammonia has become ammonium. You compare the two of them. This one has gained a proton, which will make this a base and will make this a conjugate acid. So essentially here water is acting like an acid. Now water as a base, let's do that right now. H2O plus HCl. Okay, this is going to produce that hydronium ion I showed you earlier and a chloride ion. Now let's see how these conjugates ended up working out. So H2O becomes H3O. So what's happened here? Water has gained a proton. Look, it's become H3O as opposed to H2O. So that classifies this therefore as a base, and a base produces therefore a conjugate acid. Look at your conjugate acid. This is H3O. This is acidic. This will behave or can behave like, certainly does actually behave like an acid. Now HCl, see what's happened to that. HCl has given up that proton, right? It's given it up to water. This behaves therefore like an acid in both definitions, your Bronston-Lowry or Arrhenius definitions. It behaves like an acid, and that produces chloride. An acid produces opposite, a conjugate base. So chloride is now considered a conjugate base. Now, if this reaction were to go backwards, you would see that this chloride will take up a proton, which would then follow that classification as a conjugate base. Reactions going backwards, that's something you'll learn later. Okay, not this year. So water essentially can act as an acid or a base. I put a cute little frog here because it has a similar meaning from the root word here as an amphibian can prefer, or likes actually, an aqueous, and I'm saying aqueous, an aquatic or terrestrial environment. Water can act both as a base and as an acid, hence the name amphoteric. Okay, that's it for us for now. You have an acid-base worksheet posted online. Post any questions, ask me any questions. I hope this video helps.